So this section's on planetary rings. Galileo was the first to see Saturn's rings in a telescope. Didn't quite know what they were. Um, it wasn't until, that was in the early 1600s, maybe 1610 or so. Christian Huygens, a Dutch astronomer, came around in the late 1600s and suggested they were rings. That was still in the 1600s. And then in the 1800s, James Clerk Maxwell, who gave us the theory of electricity and light and so forth, studied the rings and decided they couldn't be a solid disk. The stability wouldn't work if the rings were made of solid material, so they had to be tiny particles, which we kind of knew already because we've already seen that when things orbit the sun, the guys in the center go the fastest and they go slower and slower as you go out. So you couldn't have a solid disk that acted like that. And that's sort of what Maxwell showed. The ring systems, so all of the planets have rings, all of the gas giants, Jupiter, Saturn, Uranus, and Neptune, and they're all very different from each other. Saturn's are really big, and the other ones are really tiny. And Saturn's have sort of wide rings with narrow little spaces between them, and the other planets have narrow rings with wide spaces between them, kind of. So they don't have much in the way of mass in the other rings, and I'll give you a breakdown of that in a little bit. There are two basic hypotheses for ring formation. One is the breakup hypothesis, and this is a case where a passing asteroid or comet collides with the moon, creates a lot of debris in the explosion. The tidal forces from the planet, the things that pull things apart, just scatter that stuff around, and it makes a ring. Another way to do this is that if you have moons, like for example Io on Jupiter or Enceladus on Saturn, we'll talk about Enceladus in a little bit, spewing geysers of material out into space, that material can form rings, can be used to form rings. So the second hypothesis, that's the first one. Basically, the first one is debris gets thrown out into space through either collisions or ejections from existing moons. The second hypothesis is the unformed moon hypothesis, and that's where a material that might have formed into a moon was prevented from doing so by the planet's gravity. This is sort of similar to what happened with asteroids, the asteroid belt. The working hypothesis for that is that it should have formed a planet, but Jupiter, whose orbit is nearby, prevented it from doing so, in a similar way. So I want to talk just a little bit about tidal stability and the Roche limit. And so let me just pull up this graph here. So this is a little bit of a confusing picture, but this is Jupiter, this is Saturn, this is Uranus, and this is Neptune. And so we're going to talk mostly about Saturn. So this graph is, the solid areas are where the rings are, the dots are where moons are. This dashed line you see running down here is the tidal stability limit, the so-called Roche limit, R-O-C-H-E. It was named after a guy. If you're inside the tidal stability limit, then if you're just a loose bag of gravel, the tidal forces are stronger than the gravitational forces between the parts of gravel, and you'll get pulled apart. So on this side, you get pulled apart. On this side, you can stay together as a moon. And so a moon that crosses this line will get pulled apart. Now, there are moons that exist inside that line, but they're very small and they're pretty solid. So I said, if you're a bag of gravel, you'll get pulled apart, but it won't break up the individual rocks in the gravel. So things that are loosely connected get pulled apart, but things that are chemically bonded don't. And so you will see small moons in here that are held together by more than just their gravity. And they'll exist. They'll look like a rock of some kind. But out here you'll only see out here is where you'll see the bigger moons. And so you can see a couple of things. First of all, Saturn has a bunch of different rings, but the main rings are the A ring, the B ring, and the C ring, going from out to in. So these are all rescaled. The tidal stability limit distance depends on how big the planet is. Clearly Jupiter's the biggest one. And so its position tidal stability limit is going to be different from it's further out than smaller planets. But all these have been rescaled, so they all have the same lines. So you can kind of see them. They're not scaled to size. They're scaled to match their tidal stability limits. So you can see a little bit of a picture of the rings here. This is just sort of a sketch of the rings, but Saturn's are quite by far the biggest. Notice Saturn has rings, moons inside its rings. They all sort of do, but Saturn has them in the middle of sort of the thick part of its rings. We'll talk about that some more. So here's a picture of Saturn's rings, and you can see this dark line here is a gap, and it's called the Cassini division. And this one out here is the Encke gap, Encke. The Cassini division is caused by the moon Mimas, and I'll talk about that a little bit. The moon Mimas is not in that gap, it's outside the gap, and I'll show you how that works. And then the Encke gap, this gap here, named after a guy named Encke, has a moon in it. And so the moon is actually going through there, sort of clearing the gap out as it goes around. So let me just say a couple more things about the planetary rings. Here's Jupiter, Saturn, Uranus, and Neptune. This is just telling what the outer radius of the rings is. Notice Saturn's is larger than anybody's. The outer radius is a function of the radius of the planet, and so compared to the size of the planet, I guess Neptune's are farthest away. The total mass. So these numbers might not mean anything to you, but you can see that Saturn is 10 to the 19th versus Jupiter is 10 to the 10th. Well, the difference is 10 to the 9th, and that's a billion. So Saturn has a billion times more mass in its rings than Jupiter does. The difference between these two is 10 to the 5th, and so Saturn has 100,000 times more mass in its rings than Uranus does. So Saturn has by far the most mass, more than all the others combined, by a large amount. But a different perspective on this is to say the mass of our moon is about 10 to the 22nd, and so this is a 10,000th the mass of the moon. So from that perspective, it's not very much mass. This reflectivity number just kind of gives you an indication of what the material is that it's made of. Saturn's rings are very reflective. Uranus, Neptune, and Jupiter have a lot more dark stuff in their rings, probably organic compounds of some kind. And so they're much less visible. Even if they were bigger, they wouldn't be nearly as bright as Saturn's. So let's talk a little bit about Saturn's rings. The main rings are about 45,000 miles wide. That's from the inner edge to the outer edge. That's 6 times the diameter of the Earth or something like that. But they're only 20 meters thick. So 45,000 miles wide, 25 yards thick, 75 feet thick. It's comparable in scale to something as thin as a sheet of paper that's a mile across. So they're very thin compared to their width. There are quite a few rings. We'll just talk about some of them. Going from out to in, there's the F ring, the A ring, Cassini's division, which is that gap we talked about, the B ring, and the C ring. I'll show some pictures of those. This gives you, where their outer edge is in terms of the radius of Saturn. This gives the outer edge in kilometers, and this gives you the width. And so if I was going to do these in miles, so the F ring is very skinny. It's 60 miles wide, whereas the A ring is like 10,000 miles wide if I convert on the fly from kilometers to miles. Cassini's division is about 3,000 miles across, and so on. The B ring is 25,000 kilometers and 17,000 kilometers. We talked about the two theories of ring formation. Let me pull up here. Oops. Lost my spot there, sorry. Some of these images. Here's a good picture sort of to start with. Let me just see if I can pull it up here. Nope. There we go. Let's pull up this one. So this is a picture of Saturn, roughly to scale. And so you can see, here's the A ring out here. And then there's Cassini's division. And then the B ring and the C ring is this darker area. These were kind of named as they were found. And so it's a little weird. The D ring is very far inside, but you have to come all the way outside. This skinny little ring on the outside is the F ring. You can hardly see it. And then you can see kind of a faint G ring. And then this whole region out here is the E ring. The E ring, we'll talk in a little bit about what's populating these different rings. We believe that Enceladus, this little moon here, is spewing geysers that are feeding into the E ring. But this E ring goes all the way to Titan, which is a long way out there. And so there may be other moons contributing to that. Let me just go ahead and talk about these since they were here. So this is the moon Mimas. And it turns out Mimas creates the Cassini division. And so I'll talk about that in just a little bit, how that happens. A lot of these structure in these rings are caused by the position or motion of moons. So Mimas is one of them. It causes the Cassini division. Here is, if you look right out here at this edge, right at the outer edge of the A ring, you can see there's a little gap here. So I'm going to blow that up here. So here's that gap we were just looking at. And there's a moon called Pan. And Pan is creating the gap, the inky gap. If this is outside of Pan's orbit and this is inside of Pan's orbit, and so it's going faster than the particles on the inside and slower than the particles on the outside. So over a course of time, it sees them, it goes past them, and it pulls on them enough to disrupt their orbit and sort of clear that gap that it lives in out. And so you can get moons that cause a gap this way. You can get moons that cause a ring. So this is Pandora and Prometheus. Notice, by the way, that these look like rocks, right? They're potato-shaped. They're not a round bag of gravel. And so they're inside the rings, and they're probably pretty solid. So these two guys are called shepherd moons because these two guys are making the F ring solid, stable. And so there are all sorts of little roles that these moons play. So let's talk about these gaps in the rings for a second, just to show how they happen. So this is Mimas. This is one of Saturn's moons, and this is its orbit, right? And it's just going around minding its own business. And this is the ring, say, right? This is just the ring here, or one of the rings, or something like that, ring. And so it turns out that these are all, as we already said, just individual particles. By the way, the size of the particles is like grain of sand to a school bus. The approximate size of the particles in the ring is super tiny to chunky, right? And anywhere in between. Maybe the average is a baseball or something. I don't know. So Mimas is just going around. It's just one of Saturn's moons, and it's minding its own business, orbiting the ring, right? Well, these guys orbit faster than Mimas does because they're closer to Saturn, and if you're closer, you go faster. That's how gravity works. And so it turns out that somewhere in this ring, there's going to be a guy that orbits exactly twice as fast as Mimas does. And so that may be right here. And so when this guy goes around and does one complete orbit here, Mimas is on the other side. But then when he comes around the second time, he's back in this spot, and Mimas is right here again. If you have some other weird multiple, then when you're back here, Mimas might be over here, or Mimas might be over there, or something like that. But if you're in this spot, every 2 laps, Mimas is right there. And what that does is it gives you a little tug in the same direction from the same spot every time. And the effect that has is to clear out that orbit. If you're this guy over here, who's here when Mimas is here, then 2 orbits later, you're in the same spot again. And so over the course of time, over thousands or millions of years, you just get tugged out of your orbit. And so you end up with just a gap. And these gaps that you get in rings are sometimes caused by the presence of a moon, that's that's orbit is some multiple of the orbit of the particles in the gap. In the case of Mimas, um, this is the big gap in Saturn's rings. This is Cassini's division. Very thin rings that get shepherded by uh, by tiny moons. And so this is Pandora and Prometheus, which are actually guiding a ring around a very thin ring. Um, there are other rings in this closer view. The shepherd moon Pandora is next to the F ring, which the moon is perturbing. And so you can see ripples in these rings. So there are lots of interesting things that happen with rings and moons. They can either guide rings and make them more stable, or they can clear them out, just depending on the positions of the moons and the rings. So a few last comments. We talked about the two theories. So sometimes moons can clear out a ring. This is Cassini's division. It's been done by Mimas. Its F ring is being shepherded by Pandora and Prometheus. Enceladus is replenishing the E ring with geysers, and so let me just switch over and take a picture, show you a picture of that. Maybe not. So one of Saturn's moon, Enceladus, has these geysers going on. It's another good candidate for life existing on objects besides Earth. If I just scroll up here, you can see that's Enceladus, and it doesn't have very many craters on it. It's got a few, but it's got all these smooth areas, and so it's spewing out water. Cassini discovered this as it was flying around, and so it's possible that that there's some sort of living organisms under there as well, and it's feeding material into the E ring, confirming sort of one of the hypotheses for what's causing the rings. And just the last thing is to explain how the rings of Uranus and Neptune and really Jupiter differ from Saturn. They're almost the opposite. Saturn's rings are big rings and little gaps. Uranus and Neptune's are big gaps and little rings. And Uranus's rings were found, I think we have a picture of that. Oh yeah, here's Neptune's rings. And so very thin rings, big gaps. Uranus's were discovered by waiting for an occultation with a star. So a star sort of passed behind Neptune, even though it's a very tiny object to view in the sky from this far away. It just occulted with the star, and as the star went by, it blinked out as it passed behind the rings, and so that's how they discovered the rings. That was on Uranus. But Uranus and Neptune both have really thin rings and big gaps.